Okay, well, I'm going to go ahead and jump in. Thank you very much for being here. Really pleased to see the high turnout, especially for Unix. So, can I get a show of hands? How many people here have some distribution of Linux installed, like on their personal computer? Wow. You're not counting OSX. I mean, like Ubuntu or something like that. Okay. I am pleasantly surprised to see that. Great. And what about, so who's using a Windows machine here? Okay, great. So one of the things we always harp on is coming like from a graphical interface to more of a command line interface can be kind of a drastic, jarring jump. But the thing that's really powerful about Unix that I think we'll be showcasing today is that it is tremendously helpful for automation. So graphical environments are very intuitive. They give you menus, point and click based type interfaces. The command line requires a little bit more work on the front end to familiarize yourself with all these commands, but once you do that, the world is your oyster. I mean, you have a whole suite of really powerful tools at your disposal to do some very, very quick analysis. I want to make a couple of quick announcements before I dive in. And this is something we're going to try to do at each of these, just kind of give an update of what's new at ACCRE. So one thing is that we have a bunch of new hardware that's going to be coming online within the next probably month or so. We started asking researchers to buy nodes with a larger amount of memory. And so as a result, within probably the next month, we'll have about 50 nodes with 256 gigabytes of RAM, which is probably more than your laptop has, if I were guessing. But the great thing about that is that we often see some slightly larger queue times for users who are requesting a lot of memory, and that should help address that problem, we think, a little bit. And that will just continue to expand, I think, over the next year or so. The next thing I want to introduce very quickly, how many R users are in the house? Okay, so who's familiar with RStudio? Great. So RStudio, we recently installed on the cluster. And so you now have the ability to run RStudio from a compute node. So use RStudio like you normally would to drive analysis that on the back end is actually using the compute infrastructure at ACCRE. And so we're going to put some docs up on this on our website. Yeah, good call. Does anyone know how to, let's see. Does anyone know? Oh, here we go. There we go. Is that better?
Yeah. You all see it? Okay, good.
Okay, so this takes a couple of manual steps that you won't see here, but we're going to add some documentation to the website that will showcase this. But if you log in, like I'm on my Mac here, and I have a tool called ACCRE installed, which enables something called X11 forwarding. So you can get sort of a graphical interface from different software passed over to the network from a compute node to your local laptop. And so you log in with a -Y, if you're on a Mac at least. And just to be complete here, I'll do that. And you're going to use a tool called xalloc. So folks might be familiar with the salloc command, which allows you to run interactively from a compute node. Xalloc is the same thing. It accepts the same options, except it allows you to essentially pass a graphical interface from a compute node to your machine. So I'm going to type xalloc, and that gets submitted like just any other normal job. So you'll notice that the host name changed from CPS 11 which is one of our compute nodes. So I'm now logged in. I have an interactive session open on a compute node. And I have to load an appropriate version of R. So let's say I load version 3.2.2. And I don't remember what, RStudio 0.98. And now, fingers crossed, if I type RStudio, I should see that pop up on my laptop. And depending on, we always recommend when people are using X11 forwarding to actually make sure you're hooked up to the wall. So use a wired connection rather than using Wi-Fi if possible. something you'll see is that because of the network latency, this can sometimes be laggy. This is definitely being slower than we saw in our office. There we go. Okay, so there's our studio. It takes a little bit of time for it to, for the interface to show up, but it's pretty snappy. Our studio's not, it's relatively lightweight. MATLAB, if you try to do this with MATLAB, it's painful. It's extremely slow, and it's just not worth it. Our studio's a little bit more lightweight. If there are any Stata users, Stata's even more lightweight. So you can do this, and it pops up instantly. Yeah, don't do this outside the Vanderbilt network. It will be even slower than this, if you can imagine that. Sure.
So a user asked me today about if it would be possible to run our studio on compute node, like as same way we built it, and then to disconnect from it, all the connection, then reconnect again to the same job, to the same our studio. There may be a way. It's going to be tricky. I'm testing it. So unless you actually really need it, the answer is no. If you really need it, well, then there may be a way.
Right. Okay. So yeah, I mean, it's not super fast from here at least, but if you wire into, especially if you have a fast connection in your lab, then I think that will alleviate some of these issues. Yeah, question. Yeah. Yeah, so we talked about that in the last seminar if you weren't there. So there's a way with Jupyter Notebooks, because they run off of web browsers, there's a nice way you can just do a port forward from your laptop to your to the compute node. With, yeah, because it's not web-based, we could look into that, but not that I'm aware of. If we do discover that there is, we will definitely let everyone know. All right, so that is it for R. And the last thing I wanted to briefly mention is that we're currently building out a Hadoop-based environment, and there is a development environment that is using Cloudera Manager to manage the environment and gives you access, very nice graphical web-based access to the cluster environment to upload data and run Spark type analysis or MapReduce type analysis. So if you're interested in that, it's completely free to use. And these are tools that are widely used in industry. So if you gain experience, and if you can write on your resume, I have 2 years of experience running Spark jobs, then people will pay you a lot of money to come to their company to do the same thing. All right, so with that, I'm going to go ahead and jump into the topic for today, which is advanced Unix and Linux, or Bash, I should say. How many are here because using Unix is painful, and they want to improve some of their skills, and they just want to familiarize themselves with Linux commands a little bit more? Okay, so that's kind of what I suspected. So today we're going to be talking about some of the more advanced commands, namely ACCRE, grep, and set, that can allow you to do some really powerful processing from the Linux command line. One thing to note about Linux, and one thing that is kind of a fair question, is you have to decide when it makes sense to use Linux-based commands versus using Python or R or MATLAB or something like that. Because you'll find that a lot of these environments can do similar things. But in general, R, MATLAB, Python, these are numerical type packages that are great at doing really fast matrix operations, stuff like that. They are not so great at managing your files, and they're not so great at pulling out selected strings from sets of files and stuff like that. So when you're thinking about how to build your workflow, you might want to kind of design things around that idea. In general, if you're processing files, especially text within files, Linux is going to be your go-to. If you're doing statistics on large data sets, obviously that's never something you really want to do within Linux. But you have tools like Python, R, MATLAB, Stata that are great at that. So to start, I'm actually going to be running this demo. I'm not going to run the demo live. So this is a Jupyter notebook. And again, we talked about notebooks last time. So Jupyter notebooks, these were originally called IPython notebooks. They became Jupyter notebooks when they added support for other languages. They added support for languages like Julia and R, and now also has support for a lot of these Linux commands, which allows us to stick all these demos within a notebook and then post them on our GitHub site so you guys can go out and learn from them there. So just a note about syntax throughout this demo. Within Jupyter Notebooks, they support what are called like magic commands and cell magic. If you're not familiar with that, don't let it trip you up. You can just think of this as running from just a shell session on the cluster. Just ignore like the percent signs that are out in front. Or a percent, like this string right here, you can just ignore that and assume that this is being run on the cluster. Does that make sense? Okay. So I've been using Linux for about 9 years. I started grad school here in 2008, quite 9 years, with Peter Cummings in chemical engineering doing molecular modeling and molecular simulation. I had never touched the Linux command line before then. So once I learned it, I think I've probably used it every day since then. Having said that, I don't necessarily consider myself an expert, and I'm sure, especially with a lot of these tools, they have a huge number of options that I could never hope to memorize. So as I'm going through this tutorial, you think to yourself, there's actually an easier way to do that, or I wonder what the difference between doing it that way versus the way I've done it is. Feel free to chime in, ask a question. We're trying to make this as collaborative and interactive as possible. So yeah, I just wanted to mention that. Okay, so the first thing I'm going to do, and I'm assuming that you have a basic Linux background here, so you know what commands like cd do, and mkdir. So the first thing I'm going to do is just switch over to my home directory, and then I am going to create a demo directory where I'm just going to run this demo from. And so the second command here introduces maybe something new that you haven't seen before. And so this is essentially this double bracket notation within bash allows you to evaluate whether, in this case, if a directory exists. Okay, so I've assigned to this shell variable my printing working directory followed by a new directory called pizza and programming. I'm checking if it exists. If it doesn't exist, this double vertical bar takes care of that logic. If it doesn't exist, then it executes the next command. So that's what that double bar does. If false, execute this. So it's going to make this new directory called demodir. All right. There's also a double ampersand, which is similar. You see it used in similar contexts. It means if this is true, then execute this. All right. You'll see that a lot, like in makefiles, and when you're building software. If step 1 succeeds, then execute step 2. But if step 1 didn't succeed, then you don't want to execute the next step. You just want to stop. All right. So now I'm going to spend the majority of my talk in this next section, which is on grep, sed, and awk. Who can tell me what grep stands for? See who the serious Linux users are. Anybody? Yeah. Close. Get regular expression in print is what grep stands for. What about sed? Yes, stream editor. And awk? It's not awkward, I can tell you that. It's just based on 3 guys' names, I think. I couldn't even tell you their name. All right, so we are going to start out. The first thing we're going to do, we're going to be using a code repository that I use for a class that I teach every spring. It's called SimpleMD. It's a very stripped down, simple molecular dynamics simulator. And in my class, I use it such that it's a C program, and we start out just running it on a single core. But within the course, students learn how to incorporate multi-threading so they can execute across multiple cores. And they learn how to add CUDA support so they can run on GPUs, and MPI support so they can run across multiple different machines. So I'm just going to be using this repository for this actual demo. So the first thing I'm doing is I'm doing a set packages-a git to load the appropriate version of Git because the repository is stored on GitHub. So I can use git clone to basically download that code repository to ACCRE. And it's important to use the version of Git. There is a system version of Git installed on the cluster that is really, really old and doesn't even support like HTTPS, I think. So you always want to make sure if you're using Git to load a version via a more recent version via set packages. So once I've done this, I'm going to say something like cloning into simple MD. I can then move into that directory, and then if I run ls, I see the following. So I've got 1, 2, 3, 4, 5 subdirectories. I've got a makefile. So if you're not familiar with makefiles, maybe we can do a piece of programming on makefiles. I'll let Davide do that. Yeah. It's a tool. So Automake is a tool that allows you to automate a build process, and more commonly for C programs or, God forbid, Fortran programs. So that's what, in this case, that makefile is used to sort of automate the build process of this project. So the first thing I'm going to do is I'm going to introduce grep. So who's used grep before? Okay, so a fair number have used grep. It stands for Get Regular Expression and Print. The idea with grep in its most basic form, you can think of it as it will only return you lines within a file that contain a specified string. So if you have a big file of 1,000 lines and you only care about the lines that say foo, then you can grep foo file name and it will just return those lines. So it's a great way to filter out output within a file. And you can also pipe output to grep. You can do ls, pipe that to, do something like ls and then grep for slurm. And I have, those are my slurm directories. We'll see that. The lighting okay? All right. Could be better, I guess. So in this case, I'm running ls in my home directory and I'm piping that to grep. And this -i option does matching in a case-insensitive way. So normally grep would just return these lines down here. Because I include that -i, it's also matching that first instance of slurm. All right. So that's what we're first doing here is we're grepping for CC within the makefile. In this case, it's a case-sensitive match. And then if we run it again with -i, we get additional lines. So we get the lines that include 2 capital C's in them. So that's the difference between these two. Grep also has, again, grep has probably, 30 or 40 different command line options that you can pass it for modifying its behavior. One of the really, really powerful ones is the -r option. So that stands for recursive. And what that will do is recursively check files within a directory and run the grep on every single file within that directory. And where this turns out to be really, really handy, which I think we'll see here, is if you have a big programming, let's say you come in, you're new to the lab, and your first day in the lab, your PI says, here's an old code repository that the last grad student worked on. Go figure out how to make it work and then make it better, which is probably a very common scenario. That was my first meeting with my PI. It was 4,000 lines of Fortran 77 code. So in this case, if you run a -r, let's say you have a variable name that you're interested in. Like, oh, I see this variable is used here. I have no idea where it was defined. I don't see any comments about what that variable stores. I would love it if I could just see every instance of that variable in the programming project. Well, a recursive grep is a really quick way of doing that. So let's say I'm looking for a variable called Virial. If I do a grep -r -n, and the n here is showing the line number within the corresponding file that's listed here. And so -r is recursively going through these source files and matching Virial within any of those files. And so we see it pop up 4 different times. So that's great for variables. It's great for function names as well. If there's a function call somewhere and again you have no idea what it's doing, you can do a recursive grep to just find where it's defined. Go in and some of these projects have hundreds or even thousands of source files. So it's not trivial necessarily to easily go in and find something like that. Okay, the next thing I'm going to do is I'm going to start to do some processing on a README file within my GitHub repository. So the .md stands for Markdown, which is one of the really, really nice things about GitHub, is that you can have a Markdown file that automatically gets rendered within your GitHub repository. So if I were to look kind of at the raw Markdown, it looks like this. So for headers, you can use just a single # or hash. For bullets, you can use asterisks, and so on. You do subheadings, you can bold text. And then when this renders in GitHub, it's really nice. It allows you to build some pretty simple documentation for your project. And so this is just a description of the project layout, how to build the program, how to actually run it, and some sample output. And so this is the section that we are going to focus on. The sample output, and keep in mind this is a molecular dynamics simulation, so what's shown in the output is over time how the system is evolving in terms of its properties. So in this case, we're outputting kinetic energy, potential energy, total energy, temperature, and pressure. But you don't need to worry. If you're not familiar with molecular dynamics, that's no big deal. You could think of these could be anything. They could be features from a genomics data set. It could be, computational fluid dynamics, output from a CFD simulation, docking, economics analysis, you name it. But what we're going to do here is we want to basically do some statistics on these data. So wouldn't it be great if we could quickly gather like the average value of the kinetic energy or something like that? And so to do that, the challenge is it's sort of embedded within the center of this README file. So I somehow need to extract the relevant lines. And then once I've extracted them, I can save them to a file and use another tool like Python to analyze them. I'll actually show you how you can do some really quick and dirty analysis with ACCRE as well. But that's kind of the goal, is to extract those lines and to do something with them. All right. Any questions at all? You guys tracking with me, sort of? All right. So the first way you might think about doing it is using grep. And this is a valid way of doing it. So grep supports a couple of options, namely the capital A and capital B option that stand for after and before. And so this grep capital A 1000 is going to print the 1000 lines after it matches that string. So it's not just going to print that single line, it's going to print that single line and then the next 1000. Okay, and then, so I'm running that on my MD, on my README file. I'm then going to take that output and I'm going to pipe it to another grep command. So I'm using the output from that first command as the input for the next command, which is a grep-b 1000 simulation complete. So that means take the 1000 lines before you match that string and print those out. So what I'm doing here is I'm sort of cheating. I've used these arbitrarily large values. I know that there's not more than 1000 lines of this thermodynamic data in the output. And so I'm just printing the 1000 lines after. And then at the very end, if you recall, so I'm starting here, I'm matching that line, and I'm printing everything underneath it, all the way to the end of the file. And then I'm taking that output, and then I'm matching this line and printing everything before it. And because I've already ran that first grep, it's going to get here. This is the first line in the new output, in the input that it's reading. So basically, the result's going to be is it's going to grab these lines of text, which are the ones I care about. Does that make sense how I did that? Okay. And then I'm next going to use a tool called, so this is grep. It's like an enhanced version of grep called egrep. And I'm going to use and the reason I had to use egrep is it supports these OR operations. And the -v option is supported in both grep and egrep. And what it is a reverse match. So give me the lines that don't contain the string. And so I'm just using this last egrep just to filter out that first line that had the column headers and the last line that said simulation complete. And then finally, I'm taking that output and I'm piping it to head just for brevity. So I don't have to keep scrolling around and showing you like 100 lines of output each time I do this. All right. So that's one way to do it. And at that point, you can save it in a file, and again, you can go crazy and analyze it with the tool of your choice. You can also do it with sed. So sed is a string editor. The most common application of sed is search and replace. So if you have 1,000 instances of a variable in your project, you obviously don't want to go, or I hope you don't want to go out and manually change the name of every single one of those variables. Instead, you can do a global search and replace using sed from the command line. So that's the most common use of sed. I'm not really going to step through the syntax here. We're not really going to focus as much on sed, especially in this first case, because this is kind of a more complicated example of using sed. Not even sure I could explain it well. But sed can, all that's to say is that sed can be used often to do the same thing that grep is doing. So in some cases, they're interchangeable. I learned grep early on in grad school, and so I'm much more comfortable with and familiar with grep than I am sed, but I know folks who are just the opposite. So as an example of using a simple search and replace, you might do something like the following. So if we echoed out original line and updated line, and we just grep for pressure from MD, we'll get a line for like this. But we could also run a sed. Let's say we just want to replace the string time step with column 1. Well, the way to do that would be sed and to use this syntax. So single quote S will match the string follows the forward slash. So this is my string that I'm matching, and this is what I want to replace it with. All right. You can also do some fancier things with sed. For instance, you can, what am I doing here? Line. I completely forgot what I'm doing here. Can somebody help me out? Okay. So I've just replaced lowercase list with uppercase list in this example. So again, that's just kind of a dummy example that demonstrates the ease at which you can do kind of search and replaces with sed. Alrighty. And I've left as much detail within this notebook as possible, and it's in our GitHub organization. So if you go to github.com/ACCRE, it's in a repository called user-miss, like for miscellaneous. So these are just miscellaneous projects that we've contributed for your benefit. You can also submit pull requests to any of our repositories if you think you have something really, really useful that you'd like to share with the larger community. We would love it if you did that, actually. All right. And the last way, so we're going back now to pulling out those lines of output from within the center of that README file. You can also accomplish this with awk. I would have done this with grep for sure, but I spent some time kind of reading through awk man pages and Googling around and Stack Overflow. And there is a way to do this within awk. This is a more complicated use case of awk. So I'm not going to explain it. We're going to talk about less involved examples of awk below, and then maybe we can come back to this. Essentially, this is just, it's doing the same thing, but you can see how powerful it is in that there's a relatively small amount of code that's actually needed to do this, fairly, I wouldn't call it trivial, but I wouldn't call it super involved, but it's a somewhat complicated task. All right. So next, we are going to spend some time talking about awk. And a lot of this will just demonstrate some really useful things that awk can do. So even if you don't 100% understand the syntax and how this is working, just knowing that you have the ability to do this with awk hopefully will motivate you to kind of go back and spend some time reading through tutorials and playing around with the tool yourself. So my goal here is to print the average values of all the columns that we saw within that output. And so the first thing I'm going to do is run this same line of awk that's going to pull out, it's the same thing as here, it's just going to pull out the lines that I need. And I'm going to store that output in a file called nums.txt. I'm then just going to echo out kind of a header that indicates that I'm printing a mean and a standard deviation for each of those properties. And then I'm using awk. Awk essentially goes through your output line by line and can perform analysis kind of on the fly on each line. So it goes line by line and you feed it some code to perform some type of analysis or to process each line one at a time. All right, so in this case, we're doing we're doing one pass is in the center curly bracket, where we are taking, we're just summing up or accumulating the value in the second column, line by line, and then we're also looking at the square sum, line by line, of that second column. So the $2 just gives us the second column of data, which in this example is this right here, the kinetic energy. And then we're doing the exact same thing for each of the columns. So potential energy, total energy, pressure, or temperature, pressure. All right, so this first bracket enclosed here is a first pass through the data. Once you've done your entire pass, you can also add code to ACCRE for printing out sort of the results from that processing. So you have the ability to access variables that you used when you were passing through the data and accumulating those values. And so here we're going to print out the average kinetic energy and the standard deviation. So that's what each of these formula are doing here. One of the great things about ACCRE is that it has some built-in variables. One of those is this NR, capital NR, which stands for number of records. So it's just the number of lines that was in our output that it processed. So that's how we're going to get the mean for each of those. And then this is the output. So doing statistics, I mean, really quick, like simple things like averages and standard deviations, ACCRE can do that. But again, I would probably recommend for the most part use tools like Python or R or MATLAB or whatever you prefer to do this type of analysis. Okay. Any questions? All right. So I'll keep trucking along here. So now I'm just going to demonstrate a more simple example of ACCRE where I'm going to convert some of our temperature data from Kelvin to Celsius. All right, so I'm first storing the value of my conversion factor. I'm switching between those two units. And I'm going to use an option that ACCRE supports called -v that allows you to pass in a shell variable to ACCRE. So you can access a variable stored in a shell variable and use that for your analysis. So in this case, the variable is defined in the shell, and we pass it to ACCRE and perform our very, very simple conversion. Okay. One of the simplest things people do with ACCRE is use it just to print specified columns of data. So if you have tabular data and you only care about column 1 and column 6, ACCRE is great for that. You can just do an ACCRE print column 1, print column 6, and you're good. You're done. So that's something I did a lot as a researcher, and it's something I still do in my current position. You can also start to embed. So let's say we wanted to translate this to a CSV file. So we're using a comma as our delimiter instead of white space. You can also do that with ACCRE. So we print our first column, followed by a comma that's sort of embedded between that first and sixth column of data. Yeah. 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 I know there are tools. What would be the best tool to do that with to determine the delimiter? Some of the special characters, like an end-of-line character, doesn't show up, right? Like an editor. Right. Yeah. Yeah, you could. Right. So you could use grep. Like so grep will still see those special characters within the inputs. You could use a tool like grep, like to search for an end of line or is a tab just a T, right? It's a /T.
I mean, I think you never often talk about that. So you can use the all. Now I don't remember. There has a way to find saying at the end /T is a character. The combination itself that goes into the /T/space.
don't do that. Does anybody else have experience with that they want to share? Yeah. Right. Indentation. Yes. Yeah. That's so. If for folks who didn't hear that, you can use within most text editors, you can configure the text editor to replace things like you can map like you can change how far like your tab, does it equal one space, does it equal two, does it equal four? You can do that in most text editors. It's should be pretty straightforward in most editors. All right, so moving right along here at about 15 minutes, so I'm going to move a little faster. You can also feed awk a different field separator. So we just we just embedded those commas into a CSV file. You can also use a -F to specify what your delimiter is. So in this case, we're specifying the comma, and we're just printing those first two columns without the comma to get back to kind of a white space delimited format. So note that really awk is determining how it's printing lines based on kind of the value within those single quotes. And just to demonstrate that very quickly, if you just were to pass like a 1 to awk, it's going to print everything within that file. And that, I think I included that there because in our original awk statement where I was printing the output that was embedded in that README, it sort of made use of that fact, of that little tidbit to generate that code. You can also do things, so these are a bunch of built-in variables that I'll fly through here. So we've already seen NR, it stands for the number of records. So if you only wanted to print odd number lines, or I'm sorry, even number lines, you would do it like this. Okay, so this modulo gives you like a remainder, if you're not familiar with that. So this NR is from line to line, just incremented by 1, 1, 2, 3, 4. And if the remainder from this operation, from like a 2 divided by 2, there is no remainder. So it's going to be 0. Therefore, this evaluates to true. Therefore, the line prints. But if this is a 3, there's going to be a remainder of 1. This will evaluate to false. Therefore, the line will not print. So that's how that works. Yep, so this is just showing the odd number lines. You can also print, so you can specify things like only print lines that are greater than a given number of characters. So if you want to print that really pesky, super long line, in this case I had one that was longer than 120 characters, which I'm not proud of. You can just print the length of, the $0 refers to the entire line. So it's just saying, what's the length, what's the number of characters, line by line. NF is number of fields. So if you only want to print those lines that contain like a specified number of fields, in this particular line, those fields just correspond to words. So this is the only line within that file that contains greater than 30 words. See what else do we got here? If the number of fields is greater than 3, so let's say in this case, I'm having trouble thinking of a use case for this, but again, it's just more to demonstrate what kind of tools you have at your access here. So here I'm saying if the number of fields is greater than 3, print the first column within that field using a comma as a delimiter. All right, so make automates the build process, comma. Therefore, this was just that entire first field on that line. Finally, one thing that is often done is folks will often first grep for a string and then pipe that to awk. But you can actually do that with just a single awk command. So awk can also match strings. So if you want some grep functionality with awk, you can match strings and then print the first column within that string with a single command rather than using grep as well. All right. Any questions about grep? Or you're not allowed to ask any questions about sed because I'm pretty hopeless with sed. But it is a very nice tool, I promise. All right. Yeah. Sure. Yeah, exactly. Yeah. So he was just pointing out that head and tail are very useful for pulling out lines of text, especially in the center. So if you know like the total line count within your file, you can start and you want something within the center. You could also do like a head dash 200 to get the first 200 lines of your file, and then pipe that to a tail, and then like tail dash 50, and that would give you the the lines 151 through 200 within your file. So that's a common thing that you see as well. All right, let's talk about loops. So I'm going to assume everyone's familiar with like for loops or different variants of loops within some type of programming language. These are loops also exist within Linux, and they can be really useful, especially if you want to loop over a series of files. Pattern matching is commonly used within Linux with like an asterisk, but it's sort of limited in what it can accomplish in some cases. So an example of that is right here. So let's say we wanted to make a copy of every file that began with sim. So this asterisk, if you're not familiar with it, is just going to match any string that begins with sim. All right, so it's gonna match the simulate.sh. Let's say we wanted to copy anything that started with sim into a new file. You might think that you could accomplish that with something like an asterisk, but this definitely does not work. And the reason is that the shell actually expands these patterns before it even passes it off to the cp command. So this would actually expand to something like this, which would just fail. So if you're wanting to do something like that, file by file, rename them, then generally you do that within a for loop instead. So this is the general syntax that's used within a for loop. So the second, so you start with for, and then you pass some sort of, this would be kind of like your index variable. And you always want to give that a meaningful name. So in this case, we're looping through a couple of files. So we're doing a for file in sim_output.dat and simulate.sh. And then to enclose the lines that you want to be executed within the loop, you use a do and a done. So in this case, we're just going to copy the name of file, and this is going to be like a normal shell variable. So to access it, we have to use that $sign in front of the variable name. And then to give it a different name, say new files dash file name, it's going to make that new copy of each file. So all this is doing is for each iteration, iteration 1, file is equal to sim_output.dat, and iteration 2, file is going to be equal to simulate.sh. So that's all that's happening here. And so you can also do it using an asterisk. And in this case, we only have one file that matches. So within a loop, it's usually a really good practice before you actually execute the loop to print out what you would be executing, just to make sure you don't shoot yourself on the foot and do something you didn't intend. So here we're just going to print out what we would be printing, just to verify that it looks correct within that looping context. So indeed, we're going to run a cp simulate.sh to new files dash simulate.sh, which is what we want. You can also take just generic output from a command or series of commands and use that to loop over. All right, so let's say we want to do some analysis. As admins, we often, or at least I often do something like this. We're checking output with Slurm jobs. There's a Slurm command called scontrol show job followed by the job ID, which will give you a bunch of information about the job, including how the wall time it's requested, how long it's been running, how much memory it requested, and so on. And so here what we're going to do is we're going to loop through the output of sq -- states running. So it's going to show me running jobs, and I'm going to take the last 10 on that list and then print the first column. and we're going to use that output. It's going to be a set of lines with one string per line, so it's no different than a file. And we're going to loop over that output. And so within each loop, our job ID is going to be equal to the output of this entire sort of embedded command. And so in practice, if you were doing this, you would probably do a SQ-U, your VNet ID. Maybe you only care about your own jobs. And then I'm going to print out the following. So I'm first just showing sample output from scontrol show job. And below, what I'm doing is I'm just printing out the memory allocation for each of the jobs that I pulled out within that for loop. So for loops are definitely your friend and can be really powerful, especially when you start combining them with expressions like this.
Be careful with this for loops with a dash batch.
Yeah, be careful. If you're submitting jobs within a for loop, be very, very careful. So it's going to happen very, very rapidly. It's okay to submit a group of like 50 or even 100 individual jobs in that way. But like Davide said, be very careful. And if you're doing that, you should probably be using job arrays instead. And so some of you may have gotten angry tickets from us where we notice when someone submits like 10,000 jobs at the same time, that places a very, very heavy load on the cluster, on the scheduler, and makes it a bad experience for everyone. So we immediately, at least I immediately open a ticket. I just have a template that I copy and paste and I explain the reasons for using job arrays. And they're actually awesome, really easy to use, and we have examples on our Slurm GitHub repository if you're interested in learning more. All right, so I just have a few minutes left. I'm not going to really be able to do this section justice, but the find command is used for locating files and directories. So it's in its most simple form, you might just run like a find dot, and it's going to show you all the files and directories and subdirectories within your current directory. But then you can begin to filter that. So let's say you only care about stuff in your include directory, you might grep for include. Well, actually, probably a better way to do that is rather than running the find on your current directory, so the dot stands for current directory, you can do a find on a subdirectory. So if you just run find across include, it's going to give you an identical output, so you don't really need this grep to begin with. You can also just specify directories, so only show me the directories in my current directory, or subdirectories, I guess, or files. So maybe you want to ignore directories and only see information about files. You can also specify the max depth. So if you have a bunch of directories and embedded subdirectories that go really deep, you might only care about like that first layer. You can specify a max depth that will limit that search. And you can also specify a min depth. So if you only care about files, or if you only care about directories that are 2 levels deep from your current position, then you could do that in this way. Probably the most common way to use find is if you're looking for a particular file. You can just do a find dot and then use the dash name option followed by the name of the file, and it will return it. Another really handy option here is the dash newer. This will tell you any files that have been modified more recently than a file you specify. So show me the files that have changed since I last changed props.c. Let's see. You can also really start to do some powerful things with find, where you say not only don't only find these files for me, but perform some action on those files. So in this example, I'm changing the owner. As a user, you probably never use this command, chown. It's used for changing the ownership of a file. And so in this case, these files were initially owned by me and the group ACCRE, but I'm going to change the group to ACCRE GPU. So I'm finding any files that begin or that end with .c, and I'm changing the group who owns those files. You can also embed find. So this is very common to embed the output of a find command and pass that to another command like WC, which is a word count program. So this is saying find my header files, any file that ends with .h, and give me the line count information from all those files. All right, very short on time here. Brace expansion is something that maybe folks have seen before, and I can get through this very quickly. If you've fallen asleep or stopped paying attention, this is really handy, and will save you a lot of time. It's really easy to use. And it basically allows you to specify ranges of numbers or letters. So if you do like an echo 1 dot dot 20, it will just increment by 1 from 1 all the way up to 20. You can also specify individual numbers. You can specify a step size. And so if you want to increment by 2, you would do it in that way. You can embed these brace expansions between other characters to build like fancy directory names or file names or something like that. A really common thing that you see this for is if you want to create multiple subdirectories, you can use a brace expansion. So temp slash, this is going to create 4 subdirectories within my temp directory called src, inc, bin, and lib. You often see these brace expansions used with for loops. So if you just want to go iterate from 1 to 10 within a for loop, it's a great use for a brace expansion. You can do characters. You don't have to do numbers. It can be uppercase. It can be lowercase. You can also get some different ASCII characters that you probably don't care about, but I don't know if you did. They're there. And then you can also specify step sizes for letters. You can combine different brace expansions to again build up like something like a directory name. If you're doing statistical analysis and you're going to store a file or outputs of files in like hundreds or thousands of directories. Actually, you probably don't want to do thousands of directories, but like tens or hundreds of directories. You can start to build that up quite easily with brace expansions. And finally, you commonly see this when people are creating backups of files. So the cp command will expand the cp nums.txt space nums.txt.back. So it's a really quick way to create a backup file before you maybe do something that you'll regret. All right, so that is everything. Sorry, I kind of had to fly there at the end. Are there any we have time for maybe 1 or 2 quick questions from anyone in the audience or online? Okay, great. So you're all Linux pros. Thanks for coming. We will buy more pizza next time, I promise. And yeah, have a great weekend.